Welcome back to The Explainer. So today, we're going to tackle a really cool paradox. How can the hardest substance on Earth and, the soft stuff in the pencil be made of the exact same thing? Well, the answer is all in the invisible architecture of atoms. I mean, just look at this. On the left, you've got a diamond. On the right, the graphite from a pencil. And I know it sounds crazy, but they are made of the exact same ingredient, pure carbon atoms. And that's it, nothing else.
But here's the thing. One is famously the hardest natural substance we know, while the other literally flakes apart with just a little bit of pressure. So what's going on? Well, the secret isn't in the ingredient, it's all in the recipe, how those atoms are actually put together.
All right, so here's our game plan for today. First up, we're going to dig into what actually makes things strong in the first place. Then, we'll check out two powerful atomic blueprints, the ionic lattice and the giant covalent network. Once we get that down, we can finally solve the mystery of our two carbons and see why, at this tiny atomic level, structure is absolutely everything. Okay, so what is it that makes something strong? Really, it all boils down to the connections between the atoms, these chemical bonds that kind of act like the mortar holding bricks together in a wall.
Seriously, you can think of these bonds as the invisible glue that holds the universe together. The strength and the arrangement of this glue literally determines everything about a substance. Is it going to be a gas, a liquid, a soft solid, or a super hard crystal?
Let's see how this atomic glue can build our first type of giant structure, the ionic lattice. And to understand it, we don't need to look any further than the salt shaker on your kitchen table.
Okay, so in your everyday table salts, sodium chloride, you've got these two types of atoms with opposite electrical charges. We call them ions. The positive sodium ions and the negative chloride ions, they don't just hang out randomly. Nope, they lock together in this perfectly ordered, repeating 3D pattern we call a lattice.
And this is just a perfect example of how that tiny, microscopic order creates the world we can actually see and hold. That perfect cubic arrangement of ions on the left, that's exactly why salt forms these beautiful little cube-shaped crystals that you see on the right.
So, why is this lattice so crazy strong? Well, it's all about these powerful electrostatic forces. Think of it like a bunch of tiny magnets. The positive and negative ions are all pulling on each other from every single direction. This creates a really rigid, locked-in grid that takes a ton of heat energy to break apart, and that's why salt has such a ridiculously high melting point.
Okay, so that's one way to build something strong, through attraction. But there's another way to build a giant structure. Instead of giving and taking electrons to create charges, some atoms form these powerful links by sharing them. And this creates what we call a giant covalent network.
In these structures, you've got billions and billions of atoms, all linked together by these super strong sharing bonds. They form what's basically one single massive molecule. And of course, the ultimate example of this is a diamond.
All right, so now we have our two main blueprints for building something super strong: ionic lattices and covalent networks. With that knowledge, let's go back and finally solve our carbon puzzle, diamond versus graphite.
And it all comes down to this one simple but absolutely massive difference. In a diamond, every single carbon atom links up to 4 other carbons. This forms a tough, interlocking 3D network. But in graphite, each carbon only links to 3 others. And that small change forces them to arrange themselves in these flat, hexagonal sheets, kind of like atomic-level chicken wire.
And you can literally see what that means right here. Now, the bonds within those graphite layers are actually really strong, but the forces between the layers, they're incredibly weak. This is what allows the layers to just slide right past each other super easily. That's what's happening when you write with a pencil. You're just shearing off these little layers of carbon onto the paper. A diamond, on the other hand, is strong in every single direction. There's nowhere for the atoms to go.
So this really hammers home our main point for today. That invisible, atomic architecture, it's king. It dictates everything we can see and touch in the real world. Let me show you with a couple more quick examples. Just take a look at these melting points for a sec. Look at the giant structures, like sodium chloride and calcium oxide. They need an immense amount of heat. Now look at water and methane. They're what we call simple covalent molecules. So all the bonds inside a water molecule are strong, the forces pulling separate water molecules together are really weak. So it takes hardly any energy to break them apart and, say, turn ice into liquid water. It's all about the overall structure.
This whole idea of structure even explains something like electrical conductivity. See, for electricity to flow, you need charged particles that are free to move.
In a solid salt crystal, those charged ions are totally locked into place. They're in a cage. They can't go anywhere. But if you melt the salt or dissolve it in water, you set those ions free. Now they can move around, and that flow of ions, that is an electric current.
Now, on the flip side, most covalent stuff doesn't conduct electricity at all. Why? Well, they just don't have any free-moving charged particles. Their electrons are locked up tight inside those bonds. The one interesting exception, of course, is our friend graphite, where those sliding layers actually have some free electrons. But for most covalent materials, no flow, no go.
So yeah, the next time you sprinkle some salt or write with a pencil, just remember you're actually interacting with this incredible, beautiful, invisible architecture. And it really makes you wonder, right? If nature can create such wildly different materials from the exact same atoms, what amazing new materials could we create if we just get better at being atomic architects?